Okay, we'll go ahead and get started. Welcome
Yeah.
everyone to the Fall Semester Science of Information Seminar Series. My name is Brent Ladd and I'll be your host for today's seminar. I'm serving as the Director of Education for the Center for Science of Information. We are a 10-year NSF Science and Technology Center based here at Purdue. If you don't know about us, I invite you to visit our website, which is soihub.org. And we're pleased to host this seminar series this fall semester with today's seminar being titled The Distance Encoding, Design Provably More Powerful Neural Networks for Graph Representation Learning. And this will be presented by Pan Lee. Now, Dr. Lee just recently joined the computer science faculty here at Purdue. Before joining the department, he did a one-year postdoc out at Stanford. And before that, he got his Ph.D. in the Department of Electrical and Computer Engineering, just nearby at the University of Illinois, Urbana-Champaign. This is also one of our center partners. Both Stanford and Illinois Urbana-Champaign are both of our partners in our center. So it's really great to welcome Dr. Lee. He is working on a broad range of problems that are related to algorithms to process structured data, particularly graph and network data. His main research focuses on connecting theory and practice by developing principled algorithms, pumping up their computational efficiency, and digging out new applications for structured data processing. So we're very much looking forward to the talk today. So I'll hand it over to you, Pan.
Yeah. So thanks, Brent, for the nice and detailed introduction. And good afternoon, everyone. And thanks for coming to this seminar. And it's my pleasure to have a talk here. And let me again maybe briefly introduce myself a little bit. So my name is Pan Lee, and I'm now a assistant professor of the CS department of Purdue University. I just joined here in this fall. And okay, so today actually we will introduce a technique termed the distance encoding, which is extremely simple but effective to improve the power of graph neural network for graph representation learning. And we will provide both theoretical demonstration and empirical evaluation of the effectiveness of this method. Okay, and this is a joint work with Yanbang, Hongwei, and Yuri. Okay, now let's continue. So first, in case that maybe some of you are not familiar with graph representation learning, let me first introduce it a little bit. Okay, so graph structured data we know is everywhere, and however, because of its discrete and the irregular structure, graph structured data sometimes is hard to be used directly. So this is why we need graph representation learning, and so actually graph representation learning can handle this issue. So basically, given some graph structured data, graph representation learning is to learn some vector representations of this data so that it can be further used in many downstream applications. Okay, downstream applications. So let's first see a few applications where graph representation learning indeed helps. Okay. Yeah. Okay, so let's do this, and this is a roadmap of today's talk. And so the first application of graph representation learning is for node structure role learning. So basically, given a large graph, we want to know how each node contributes to the structures of the graph. Okay, the contribution a node makes can be viewed as the structure role of this node. Okay, so let's consider an example here. We have a co-authorship network, and each node corresponds to a researcher. And if two researchers collaborate with each other, then there will be an edge between them. Okay. And in this network, the nodes can be roughly characterized into 4 different ways to contribute to the structure of the network. And there are some bridge nodes highlighted as this right diamond here, and they represent the central and prolific researchers. And the nodes highlighted as a green square here are the neighbors of this bridge node or this right diamond node. Okay, and green triangles refers to the researchers that are kind of peripheral in this network, and the blue circles here represent the authors or the researchers that has a lot of co-authors and are kind of have a homophilic neighborhood. Okay, so there are 4 different structure roles of this nodes. And to identify these structure roles of different nodes, essentially we may use graph representation learning. And graph representation learning will map the contextual subgraph around each node to some vector representations, which actually encode their structure role information. Okay, but note that possibly for 2 nodes, although they are far away from each other in the network, and they may have the same similar structure roles. So graph representation learning may associate this type of nodes with a similar representation so that we can have the similar type of inference for this node. Okay. And the second type of application of graph representation learning is to make link prediction. And we can use the link prediction to recommend, let's say, friends, or figure out potential collaborations in a social network, or even perform item recommendation in an e-commerce system. Okay. And since we want to perform this link prediction, and which is relevant to a pair of nodes, and graph representation learning allows us to extract the structural representation for a node pair from its contextual graph, which can be further used to decide whether there could be a link between this node pair. Okay, between this node pair. But be careful that there are a lot of traditional methods to do this link prediction and or something terms matrix completion. So in the recommender system, but this is a different approach. So here we are not used to this kind of traditional collaborative filtering method. Here we use the contextual structure of a node pair to do the job. Okay, to do this link prediction. And of course, graph representation learning can predict more than just links. So it can also predict the higher order structures. For example, if we can use it to predict whether, let's say, the 3 proteins may form feed-forward loops from its based on its the information embedded in their contextual graph. Okay, we can do this higher order link prediction. And more than that, we may also use graph representation learning to get the representation of entire graph structures, such as molecules, and so that we can use this representation to predict their properties or maybe classify this different type of molecules. And of course, we can also use graph representation learning to do some fast search of the different graph structures. Okay, so just we want to find the graph structure that share the similar type of structure. Okay, now you see there are a lot of applications that can be done by using this graph representation learning. Now, next, let me give a formal definition of the problem. That it's actually a mathematical description that is extracted based from the previous application. So basically, we will have a bench. So this format of input data. So basically, we will have a collection of 2 tuples. Okay, and in each tuple, the first component here corresponds to graph structural data. Okay, know that this A here could be either a single graph, such as correspond to a molecule structure, or it could be a subgraph extracted from a large network. Okay, so maybe the contextual graph around a node or around a pair of nodes. Okay, and of course, so this graph, let's say structural data, this tensor A, so it may contain this adjacent matrix, which can just view as a slice of this tensor. And the other dimensions may correspond to some node and other features or attributes that you may have in this graph structural data. Of course, all of this just depends on your applications. So whether you may have this attribute or yeah. And the second component in this tuple is of this tuple is a node set that we are interested in. Okay, we are interested in, and the size of this node set could determine by different type of applications. So it could be a single node, so which used in, let's say, node structural role learning, or it could be a node pair which used for link prediction, or maybe in some high order sense, or even includes an entire node set which used for molecule classification. Okay, and graph representation learning is basically the formal definition is to learn a mapping that from this two tuple to a vector. Okay, so and this vector, you can imagine this representation FAS kind of captures the relative information contained in the structure A and the target node set S, and that used for certain type of applications. Okay, of course, I would like to say is different applications may have different requirements of this representations. So basically, in our setting, the specific representation on this learned representation is data-driven. Okay, but we actually may expect two generic requirements on the representation that we want to learn. Okay, what's these two requirements? The first requirement of this representation is that we want it to be invariant. So what do I mean by the invariance here? So basically, if for two tuples, A1 S1 and A2 S2, if you can find a bijective mapping between the node sets of these two graphs to make these two tuples same to each other, we call these two tuples isomorphic. And if these two tuples are isomorphic, we expect that our model will assign the same representation to them. Okay, so this is called invariant. This is called invariant. So an example of this invariance, let's say of this invariant property is shown here. So basically, we want to suppose we want to predict whether there could be a link between these two nodes and this two nodes. Okay, so these two nodes, and since they are isomorphic to each other, so basically you can find a pi to have this mapping here. So they essentially will have the same representation. Okay, so if your model satisfies this invariance, then they will have the same representation, and therefore they will have the same predicting result. Okay, so because they are totally equivalent to each other, so there's no sense to distinguish them or have a different representation for them. And from machine learning perspective, this, let's say, invariant property is very important. First, it is very important for inductive learning. And as we may expect to train our model, we're using certain part of the network and apply our model in another part that has not been seen during the training. And for this, so this is for if your model is able for the inductive learning, then the pattern in the testing data set. So you applied your model here in the testing data set that has the same, that is the same as the one that you encounter in this training data set. So they should share the same representation. Okay, so an inductive model should satisfy this property. Okay, and another property is basically if you have so this invariant property is also good for model generalization. Okay, as the models that are invariant essentially allows certain parameter sharing, which means the models will have the parameters to process different parts of the graphs. Okay, so this actually can significantly decrease the dimension of the model, which can make your model not, let's say, that easy to overfit the data. Okay, so this is good for better generalization. And the second requirement of the representation that we want to learn is its expressiveness, which means if for two non-isomorphic, let's say, structures, okay, we expect to have their representations different. Okay, we expect to have their representation different. And maybe this requires, at first, you think it sounds a little bit weak, but however, it's not that weak. Okay, so especially in our data-driven scenario, so that is the good thing is we may prove that as long as the learned representation can distinguish non-isomorphic tuples or structures, we may expect a neural network that can transform this representation we learned to approximate any continuous invariant function defined over some compact space. So basically, in practice, maybe you want to approximate any, let's say, an arbitrary type of invariant function, but as long as our learned representation is able to distinguish non-isomorphic structure, then you can always approximate that mapping. So this is really good. So basically, this requirement is not weak, especially when we have this data-driven, let's say, setting. Okay. And overall, to summarize that, we need two requirements for this graph representation learning. So at first is perhaps for you, if you are familiar with some, let's say, the terminology graph isomorphism testing. So at first, these two requirements just sound like graph isomorphism testing. Yes, if we have this set, this target node set, so basically the second input here as an entire node set. So then there's two requirements reduced to graph isomorphism testing. However, for practical usage, graph representation learning have different aspects to emphasize as opposed to graph isomorphism testing. Okay, and actually, from machine learning perspective, graph isomorphism testing can be viewed as binary valued graph kernel, and this graph kernel we know is not continuous, and thus will have a very bad generalization property. And itself is hard to compute, as we know. Until now, we don't have a polynomial algorithm to do this graph isomorphism testing. So even you just want to compute this binary valued graph kernel, you will not have a polynomial type algorithm. Okay, and graph representation learning here is actually we'll learn explicit feature map based on this structure. Okay, and this feature map is parameterized and learnable, and it can be totally data driven. So and usually if you use let's say a neural network to implement this mapping, then it's usually smooth. Okay, so it's usually smooth or at least continuous, and thus good for generalization. And it's because it's explicit feature map, it's usually easy to be computed. Okay, to be computed. Okay, and overall, to summarize all about, so our goal is actually to keep the invariance of this representation, but in the same time, we expect to have a representation that is expressive enough to distinguish, let's say, different structures or different tuple. Okay, and we also expect that it's for practical usage, it could be computationally efficient and applied to the large graphs. Okay, large graphs. And there are different ways to compute the graph representations. And in this lecture, we will particularly focus on graph neural networks and the recently widely discussed tools to compute this representation. Okay, and we know some previous kernel methods also allows for graph representation, but they just aggregate and account different type of graph features. And usually these features cannot be computed in a very efficient way in practice. And the counting procedure is not parameterized, and therefore lose some freedom to feed the data. Okay, feed the data. But we just focus on the graph neural network to compute this graph representation learning, which could be very efficient and have the freedom to feed the data. All right, now let me briefly go discuss about the graph neural network for the graph representation learning and introduce their limitation. Okay, and for graph neural network, usually we will have a graph structural data. Here is A, and we have node set S of interest. And graph neural network will follow this method passing way to compute the representations of this AS pair. Okay, so first it will initialize each node here with a vector representation according to their own features, and then ask each node to aggregate the representation from its neighbor, and each node will further combine this aggregate representations to update its own, let's say, representation. Okay, graph neural network just iterates this way. Okay, by using different layers of graph neural network and to iterate the layers. And finally, graph neural network will read out the representations of the nodes in the node set via aggregation operator to have the final representation. Okay, of course, this final representation FAS will be compared with some ground truth label to compute the loss, and we will minimize such empirical loss by optimizing the parameters in this model, in this graph neural network. And where is that? So actually the parameters is contains in this alpha update function. Because usually this alpha update function is just like a feed forward neural networks. Okay, feed forward neural networks. And the aggregation operator here will remove the effect of the input order of the elements, and this makes the let's say the final representation we learned is invariant to the input. Okay, to the actually the order of the node. Okay, and this procedure actually includes many widely used graph neural networks, such as this graph convolution network, graph stage, graph attention network, graph isomorphism network, and the master pathing network, etc. Graph neural networks are powerful and have shown their success in many applications. However, their expressive power has limitations. Okay, actually, it is not hard to show that the expressive power of graph neural network is bounded by some very traditional method called one WL test. Okay, one WL test. So basically, so what do I mean by bound here? So basically, for any structures, if one WL test cannot distinguish them, then graph neural network, by following the previous procedure, cannot distinguish them. Okay, so this could be proved in a very easy way. And therefore, it means the graph neural network will generate the same vector representation for many structures, although they are not isomorphic to each other. Okay, and here I also would like to remark a few recent works that are trying to break this limitation by proposing more powerful graph neural networks by mimicking higher order WL test, but all of them will transform this the original graph into a fully connected one, which makes the problem the algorithm not that scalable. And this method only evaluate for the entire graph representation. Okay, so which means our target node set S equal to the entire node set B. To better understand the limitation of the graph neural network, here I gave one example here. So suppose we want to distinguish the structural role of the two nodes. okay, in the two graphs. So via a two-layer graph neural network, okay. So and so as a definition for the structural, so we want to distinguish based on their let's say contextual structures here, okay, their contextual structure here. So we may expand the computation graph of the graph neural network just to follow the iteration procedure in the graph neural network to compute their representations of these two nodes. And you can easily see that if we have a two-layer graph neural network here, the computation graph, which essentially corresponds to the subtrees with height 2 rooted as two nodes. So this computation graphs are exactly the same, okay? So we may not distinguish them. So although they, in the left figure, you can see, obviously they have different structures, okay? So, but two-layer graph neural network cannot distinguish. And of course, you can follow the previous procedure to show, okay, graph neural network will also fail in these two cases. So one, even it, we have infinite layer here. So graph neural network cannot distinguish the two node pairs here. Then it will fail to make any link prediction here. And the graph neural network also cannot, let's say, distinguish these three regular graphs, though they have different structures, okay? So this is all due to the fact that graph neural networks, its representation power is bounded by 1W10. Okay, okay. So now finally we come to our solution. That is the distance encoding. And how can we use the distance encoding to solve all the previous problems? Distance encoding in general is actually is a very simple way to improve the representation power or expressive power of graph neural network. In general, it's just first compute some structural features for each node V that based on the target node S and the structure A, and then we will so we will have this. So this is a distance encoding, and then we just plug in this distance encoding into the graph neural networks in a very naive way. So how can we do that? So basically, in the initialization procedure of a graph neural network, we will concatenate this distance encoding to the initial features of the node, okay, of the node. And if we may set the distance encoding to be invariant to the node orders, then the obtained final representation will also keep the invariant property. So basically satisfy our first requirement, okay? And then the next question. So that's the previous definition, very general. So so what's the specific distance encoding we see? Works that is very powerful, and this is the definition. Okay, essentially we will set the distance encoding for each node U as a set of distance encodings between this node U and any node V in the target node set S. Okay, in the target node set S. And this distance encoding between the two nodes are defined as a mapping of landing probabilities of random walks that start from this node V to this node U. Okay, to this node U. Note that this actually may be a little bit complicated, but it actually so the intuition behind it is just characterize some distance measures between the two nodes, okay? Distance measure between two nodes. So this general definition covers many specific cases we are using, let's say, based on different type of mapping G here, okay? It includes something like this shortest path distance between these two nodes U and V, or heading types of the random walk. Start from V and land at U, and also personalized page rank scores between U and V. Okay, so just based on different type of specification of this for mapping G, and you will have a very simple version of this distance encoding. All right, and based on this definition of distance encoding, we can just let's say pair the graph neural network with this distance encoding, and we call this obtained model as DE GNN. Okay, and note that in practice, the computation of distance encoding will in general not introduce much more overhead, because in practice we show that we find that usually you just need to do at most 3 to 4 steps of random walk to compute this distance encoding, then you are fine. Okay, then you are fine. And although this distance encoding technique is very simple, it could be extremely, let's say, effective. Okay, let's first see the theoretical characterization here. So basically, we may prove that for 2 structures, if the target node set is of, let's say, constant node size, then we may prove that for almost all n-sized R-regular graph, this model, this, let's say, DGN, may be able to distinguish these 2 structures, okay, within 0.5, about 0.5 times log n over log r number of layers, okay? So with this many layers, our DGN can distinguish these 2 structures, okay? And of course, the previous definition of the distance encoding also keep the model permutation invariant, okay? But maybe your question is, you may wonder why we choose this regular graphs. So in the regular graph, each node all the nodes share the same degree. Why we choose this special case to demonstrate all the theoretical results? Because this is a case when all the standard GNNs without distance encoding will fail. Okay, so because of their power is limited by 1 WL test, and 1 WL test cannot distinguish the structure here, so all previous standard GNNs will fail to distinguish these 2 structures. But our distance encoding assisted, let's say, graph neural network can do that job, okay, with high probability. And let us see how it works in a specific example. Let us just go back to the previous node representation learning example, where we are trying to distinguish these 2 nodes based on their contextual structure. We are a 2-layer graph neural network. Okay, we know that standard graph neural network will fail because they share the same computational graphs here. Okay, yeah. So, but if we plug in their distance encoding, we can distinguish them. And here we just, for simplicity, we just use the shorty path distance to the target node as the distance encoding. Okay, and they are labeled with different colors here to denote this distance encoding. And then if we further expand this computation graphs, we see the difference here. Okay, that there's a difference appearing here, which allows us to distinguish these 2 nodes with these 2 layers. Okay. Of course, another example is to perform this link prediction here, where graph neural networks, standard graph neural networks, even with infinite layers, we cannot distinguish them. But if we pair it with distance encoding, we can distinguish these 2 settings. Okay, these 2 settings, these 2, let's say, node pairs. But note that here currently the target node set is a pair of nodes, so the distance encoding is also a pair of shorty path distance. Okay, from this node to this 2 nodes in the target node set. Obviously, the 2 target nodes will generate different distance encodings as shown here, and of course they can be, let's say, distinguished. Okay, these 2 node pairs. All right, and we also evaluate this DGN in a more extensive way over some real networks. We evaluate over 3 different tasks, including this node structure row classification, link prediction, triangle prediction, and these 3 applications require us to learn the representations of single nodes, node pairs, or node triads, respectively. Okay, and all these applications here are so all the baseline here, are either the standard graph neural networks or kernel-based method. Okay. However, it's our distance encoding is able to significantly outperform these baselines, and in general, the improvement is about 5 to 15%. Okay. And before ending this talk, let me briefly introduce about some. So we have already seen the power of distance encoding, and next let me briefly introduce the limitation of the distance encoding method. So, and to learn, we know to learn a graph representation that may distinguish all non-isomorphic structures is at least as hard as graph isomorphism testing. So we are not expected to, let's say, solve this graph isomorphism testing problem. So there must be some limitation of distance encoding. And to investigate this limitation, we focus on the case when the target node set is just of size 1, okay, of size 1. So so basically, we want to learn the representation of the single node. Okay, we focus on this special case here, and here's the result. Actually, we may prove that if we don't have discriminatory node and edge attributes, distance encoding may not learn distinguishable representations for each node of over the distance regular graph with the same intersection array. Okay, but I will not introduce the definition of a distance regular graph. Interested audience may just, if you are interested, you may check the literature at least here. Okay, at least here. So, but a high-level understanding about distance regular graph is they are just a special case of the regular graphs, and they may have more symmetric structure here. And here are two distance regular graphs with the same intersection array, while they are actually not isomorphic. Okay, so these two structures are not isomorphic, but distance encoding cannot help us to, let's say, distinguish the node here. Okay, the nodes in these two graphs. Okay, so there are more implications regarding the limitation of this distance encoding. Because of the general definition of the distance encoding, we may prove that quite a few empirical successful techniques to modify the current architecture of graph neural network will share the same limitation as this as a statement I showed in the previous theorem. So one commonly used technique is to aggregate multi-hop neighbors simultaneously. Okay, but when performing this aggregation, representations of different hop neighbors will be associated with different ways. Okay, with different ways. But some specific models that built on this technique include this mixed hop or PGTN, and we may prove that all of them share the same limitation as the statement I showed in the previous theorem. Okay, they show that so even you do this multi-hop aggregation simultaneously, you will have the same limitation. Okay, and there are also some other works that perform type of graph diffusion over the network over the graph to aggregate node features. Okay, so basically in each layer, we use this different powers of some type of matrix here to propagate node features. Okay, here H is the T layer node features, and this is T+1 layer node features, and this is just based on different matrix to do the propagation. And this matrix could be adjacency matrix, normalized adjacency matrix, Laplacian matrix, normalized Laplacian matrix, never mind. So you can plug all of them in. So this covers a lot of models, techniques proposed previously to improve the power of graph neural network. And we show that they actually share the same limitation as I showed in the previous theorem. Okay. And but I also would like to mention an additional remark here. Although we have the limitation of distance encoding for the single node representation, however, if we use a node pair as our target node set S and compute the distance encoding based on this node pair, then our distance encoding technique may provide some extra power. Okay, we may show that if we use a node pair as a target set to compute this distance encoding, essentially we can distinguish these two graphs and any two node pairs in these two let's say, distance regular graphs. Okay. Cool. In the end, I have finished all the content here, but in the end, just let me briefly mention some future works that can be done regarding this distance encoding. Actually, we may prove that the distance encoding also improved the graph neural network for entire graph representation learning, which is widely used in molecule classification or property inference or molecule property inference. However, we have not empirically evaluated them in this project. While we expect that distance encoding may indeed help this entire graph representation learning in practice. So if you're interested, you can look into whether to how we can use this distance encoding technique to, let's say, get a better entire graph representation learning. Okay. We also hope to see tighter, from theoretical point of view, we also hope to see a tighter analysis of the successful probability of this distance encoding technique to distinguish structures in a regular graph. Okay, so currently the successful probability, if you still remember, is something like a 1 minus 1 over n. It's independent of from the size of the target node set S. But actually, we have seen that the representation power or the expressive power could be, let's say, improved when we have a larger target node set S. Okay, and we also see this gain empirically. But we guess it's the successful probability, if we can have a tighter analysis on that, it also should depend on the size of target node set. But we leave this problem for the future study. Okay. Okay, so I have now finished all my talk, and I would like to take take questions. Yeah, for this. Thank you for your attention.
Thank you, Pan.
Yeah.
Yes, excellent. Any questions or comments for Pan? You can either type into the chat function there, or you could press your space bar to ask a question. And Pan, can folks contact you offline, maybe through your faculty page? I think probably you have your email there.
Yeah.
Yeah, sometimes.
Yes, yes. I will put my email in my webpage, so that's
Okay.
So people, yeah. Mm-hmm.
Okay. Yes. Okay. Well, if no one has any questions or comments at this time, we're recording this, so we'll have it up on our YouTube channel too. And if anyone thinks of anything in the future, they can get a hold of Pan that way. So welcome again to the department, Pan. We're happy to have you at Purdue.
Yeah.
And anyone interested in our continuing series, we'll be back in 2 weeks from today with another fairly recent faculty member at Purdue, Maji Hamanta. So with that, thanks again, Pan, for presenting today, and we'll see you next time.
Yeah, see you. Yeah.
Okay. Everybody be safe and well. Thank you.
Thank you. Bye.